Hello, Bojana.
See?
Let's start. Today is our last class.
Okay, can you see it now? Do you see it? Okay, thank you. Good, so welcome to the third class, the last class of the course. So in this class, we will join different structures that we have defined and introduced in the previous class. Okay, so this is this part here below. Today we will see internal categories. We will define them as specific to monads. This is so by Benaboú. Then we will see enriched categories and when they induce internal categories. We will see two monads in the bicategories of spans and matrices. And finally, the double category of monads, and I will show you why vertical morphisms of monads are useful. So we start with internal categories. As I say, this is also by Benaboú. And C, for this, to define internal category in C, this C is required to have pullbacks. Now, the B category of spans in C, we saw at the first class when we defined bicategories, this was one example. And now we come back to it. So I recall here, 0 cells are objects from C, 1 cells are spans, which are diagrams of this form. So for 2 0 cells or objects in C, these are A and B, a span is given by this additional object and two morphisms in C so that we have this diagram. And 2 cells are commutative diagrams of this form. So for one span here and another here, the 2 cell is given by this morphism F in C so that these two squares commute. And now a category internal in C, where C has pullbacks, is defined to be a two-monad in the bicategory of spans. So now let us translate what this means. First, in general, I recall here a two-monad in a general two-category K. It consists of a 0 cell A, two endo one cells, one endo one cell T that acts on A, and two cells mu from TT to T and eta from identity on A into T, such that these two axioms hold, one saying associativity of the multiplication, and then here the unitality of multiplication. So now let us apply this two monads in this bicategory of spans. So we go by step by step. A 0 cell in A. So 0 cells in the bicategory of spans were objects in C. So take one object in C and let us denote it by x0. Then we need a 1 cell T from A to A. So 1 cells in the bicategory of spans are these spans or diagrams where we put on the same 0 cell and we fix this object x0, we put it in the both extremes. And then this 1 cell is given by an additional object x1 and two morphisms in C, which let us just denote by S and T. So you may see here already the intention to adjust it to the form of an internal category. You saw it only for the category of categories, but the notation is universal. And finally, we ask for two cells, mu and eta. So now since T is this span diagram, then TT is the composition of these two spans. So this is in the domain. So I put it here on the top. So you see here that we have the pullback, right? The composition of two spans is given by pullbacks. This we saw in the construction of the bicategory of spans. And the codomain is T. So this span here. And so I put it here below. Now the 2 cell comes given with some morphism from that pullback into x1, and let us denote this morphism by C. And then we know that these two squares should commute. And for the two cell eta, so it should start from the identity on A, but A was the object x0. So the span identity on x0 is given like this. We also commented that. That's the domain for the two cell eta, and the codomain is T, or this span here below. So now eta is given by a morphism U that goes from x0 to x1, and so that these two squares commute. Now, I did not comment, I just said that here, when you here see this two cell mu, which is given by the morphism C from the pullback into x1, I did not comment you why we have these two morphisms towards x0, TP1 on the left and SP2 on the right. Well, this I comment in this diagram. So I said that we had there the composition of two spans, of this span with itself, right? This composition is made so that you take the pullback here of x1 with itself over x0. Then we have these two projections, P1 and P2, and the composition span is made by so you put the object, which is pullback, in the middle, and then these two morphisms, P1 followed by T and P2 followed by S, and this is precisely what we have here on the top for the two cell for mu. Okay, and we also require that C, the composition on the pullback, should be associative and unital with respect to that morphism U. And now also from the commutativity of the diagrams for the two cells mu and eta, yeah, we also have these compatibilities. Okay, these here. Okay, so sorry, let us sum up. A category internal in a category C with pullbacks consists of, so firstly, we took an object x0, and one calls it the object of objects. And then at the next step, we took another object x1, which is called object of morphisms, and we also took two morphisms, one S, another T, from x1 to x0. So these morphisms will be called source and target that go from the object of morphisms to the object of objects. And finally, we had two morphisms more in C. One is C on the pullback, and the other is this unity, which are associative and unital. And moreover, these are these compatibilities of source and target with the composition and unity. So this sums up what an internal category in any category with pullbacks is. We saw when we defined in the last class double categories that they were internal in the category C, which was cat1, the category of categories. And then we had this similar thing but applied to this category. Examples, this first example that I put here is a category internal in the category of sets. This will give a small category, and let's see why. I mean, it's easy, but still I want to show. So we have two objects in this category, so two sets. And in order to recover category C, this first set S0 will be that of objects of C. So the class of objects is set. That's why I have a small category, okay, and not any category. And the other one, S1, is given by this coproduct of the home sets. And then the source and target, okay, so they map from S1 to S0, units the other way around, and composition is given from that pullback. But now, by the definition of morphisms that go, that start from coproducts, and also that end up in coproducts, you know that all these four morphisms are actually given by some other four morphisms where I just leave out these coproducts. And by abuse of notation, I will use here the same notation on the morphisms. So from the home set, home from A to B, to the set of objects of C, I have the source and target. Then unity to every object, I put an identity Yeah, okay, so it should be AA, and the composition like that. The next example, I put here a category internal in the category of categories. Yeah.
Yeah. How do you define correctly C? Because the coproduct is a co-limit, and then you are creating a arrow entering in this co-limit, not getting out of this. How do you do this exactly?
Yeah, the one that gets out. Yeah, I mean, okay, I will explain what I meant with what I said. The one that goes out, of course, is defined on the thing without coproduct, right? So only on home. No, so that's where we agree. Your question is when it gets into a coproduct, right? So, for example, the U should end up in the coproduct of homes. So what I do is I give U that ends up only in one copy of home, and then I just embed this one home. I embed by these, I don't know the name for projections or what's the word, in the coproduct.
Yes, I understand what you do component-wise, but this arrow defined on the objects are well defined, both U and C. This is my question. As well as a
I mean,
function.
why they will not be? Because these are sets, and there we have limits and co-limits. Small sets are in question.
No, yeah, yes,
I mean,
but
like which precise point is the problem that you see?
yeah, no, yes, as uh, because limits, for example, you can define things in the product entering. For example, if you define something entering the product of homes, it would be well defined because then it's the universal property of the product. But here you cannot use the universal product. In how do you, from component-wise definitions, you raise up to that definition of U and C? This is perhaps is silly for my question, but I cannot see. Perhaps it is because it's in set, then you can more or less put this, but uh, I'm not
So
totally
for
sure.
example, C is coming out of the coproduct. So this upper C, I don't know if you see this mano, the hand. And then the C below is just given on that one component, so to say. So,
Okay, I would not insist much
I mean,
because
if
I'm
you
not
have
totally
a,
sure.
I mean, here I'm not really, how to say, I'm starting with a category, and then I know that I have this C at the bottom, so I know that I have it. And then once I have it, and I know that the coproducts in the category of set exists, so I have these iotas or coprojections, and then I know that there is one unique morphism, which I also call C, that comes out from the coproduct, and it ends up in the home AC. But then I compose it with a coprojection that goes from home AC into the whole coproduct.
Okay.
This is what I do. If you think that this is not correct, then maybe we can speak later in order now not to make a big break. But I think that this is okay.
Okay.
And I will
Thank
have
you.
a similar diagram, how to say, soon. And I will, draw it so visually we can maybe, see the same question there. On another example, but the concept is the same. Okay. Okay, so here the next example is the category internal in the category of categories, and we saw that it is a double category. The last example that I write here is a category internal in the category of topological spaces with the morphisms are continuous maps. And this, when one sees it, is a topological category. Well, I'm not an expert in this, so I don't know to say much, but it's I just list one example. that there exists. Okay, so now I want to speak about enriched categories, which I guess everybody or almost everybody knows, but we will use it. A category tau is said to be enriched over a monoidal category C. If I don't see over or enriched over a monoidal, but I just say a category, then I'm assuming that it's with Cartesian product monoidal. Okay, but in general, C should be monoidal. So now firstly, object of tau is a set. Then for all objects, this home set in tau, it itself is an object of C. Then the map that gives composition in tau is actually a morphism in C. And there is a morphism in C that goes from the unit object of this monoidal category C into the home set AA. And it is required that this C is associative. And since S is a morphism in C, to express this associativity, we are using this tensor product from the monoidal category C. And this C is also unital with respect to this J. So these are two morphisms in C. And for that, we also involve these lambda and rho unity constraints of the monoidal category C. Examples, the first ones that I list here are the categories of abelian groups, modules over, say, commutative rings, the category of vector spaces. They are all enriched over themselves. Well, we already know that when we treat morphisms among groups, we want them to be group morphisms. So actually, this home set itself has the structure of a group. And the same happens for our modules and vector spaces. So there we have this linearity with respect to R and K. And okay, so all the structures so that you have indeed an enriched category. People are not always saying this, but this is a fact in the background. A category enriched over set is a small category. This is, enriched is a small category. So if you take that the object of your thing category should be a set, so it already can be a small category, but then the home set is indeed a set. Well, this indeed happens in a category and so on for the composition and unit. A category enriched over cat1, well, I say here that it is a two category. So we have that like the basic thing that one sees is the home set. So the home among two objects in this enriched category should be a category. So if your home set is a category, we define precisely two categories and bicategories this way. And now you see when I say enriched over cut, I didn't say which is the monoidal structure, where I mean the Cartesian monoidal structure. And then it is strict. So the alpha, lambda, and rho are identities. So then this composition C should be associative and unital strictly in the strict way. And this tells me that I have indeed a two category and not a bicategory. The next example that I put here, I put in purple or lila because it's actually category enriched over a two category. And I already said what is enrichment over a one category. So here we have one dimension more. But since when you look at home sets and the composition, you will have same things as in the previous example. So the home set will be a category and the compositions will be a functor. And also cat2, all the two category, it is Cartesian monoidal. So at the first glance, you would say that alpha, lambda, and rho are identities. So we could have strict associativity and unitality, but actually not, because when you draw these diagrams for C and this J to be associative and unital, since we have enrichment in a two category, then when you draw the diagram in one category, you normally just require an identity to hold. But in a two category, when you draw a diagram, you fill in that space inside of the diagram with a two cell. So then when you express in diagrams associativity and unitality, you require to have a non-trivial two cell which controls the associativity and unitality. So this is why enrichment in the two category of categories gives a B category and not a two category. Okay. So I wanted to, just you to have this feeling about what happens when you add higher dimensions. This last example, I will not explain in the detail, but I just want you to hear it. Category enriched over this pseudo double. This is a two category of double categories with some particular morphisms among double categories, which are called pseudo double functors. Well, this kind of thing, Garner and Gursky, in some work of them, they call them locally cubical bicategory. And on this slide, I want to say what are enriched functors, because we will come back to this. If F acts between two enriched categories tau and tau prime with these structures C and J, then this functor is C enriched if these maps are actually morphisms in C and they are compatible with the compositions of tau and tau prime in this way and with the unities. These compatibilities or equalities are as of morphisms in C. I will use diagrammatic equations later on, so I just translate these two axioms in diagrams. They're not string diagrams, but with these boxes. In the box, I write the name of the morphism. Here C, here F, and so on. And the objects are these tau, of course, right, for the composition. Okay, so now from enrichment to internalization. Let's see what happens here. Well, we already saw that a two category, respectively by category, embeds into a double category, here is meant in strict sense, respectively in a pseudo double category. So in the last class, when we defined double categories, we saw that as I wrote this diagonal, there I put the bicategory, and on that contra diagonal, I put this vertical one cell. Well, stated in other terms, a category enriched over cat1 that we just discussed, it is a two category, embeds in a category internal in cat1, which we know that it is a strict double category. And now in the weak context, because it involves enrichment and internalization in the two category and not in one category, I put it in lila just to stress the difference in dimension. So this is for this bicategory embeds into pseudo double category. Stated in other terms, a category enriched over cat2 that we just saw, it is a bicategory, embeds into a category internal in cat2 that we saw in the previous class that it is a pseudo double category. Also for that last example from the previous slide of Garner and Gursky, a category enriched over that two category was shown in the work of Grandis and Paré. They introduced the notion of intercategories, which are internal in some other two categories of double categories. Well, when you see their argument, you recover actually that this enriched category over this pseudo double is indeed category internal in this same two categories. Now, actually, a remark why I'm saying this to you. Now, in this talk, I just want to speak about internalization and enrichment in one category. But in my last research, there is an archive, I have studied based on these examples and also in an example in three categories, that this embedding of enrichment into internalization, so to say, put informally, I have also on the level of three categories. So then I proved under which conditions this happens in three categories. So that's why I put these things in lila, but you can forget it now. And we come back to the one-dimensional case. Well, actually, there is a theorem. It says Erisman and Erisman because one is André, that's a woman, and Charles is her husband. In 78, they proved under this list of conditions, a category tau which is enriched over a category C is internal in that same category. So now I will command the list of conditions. Assume that C has finite products, terminal object I, and small coproducts. Suppose that tau is enriched over C. Then set T0 to be the coproducts over the copies of the terminal object. And suppose or set define that T1 is the coproduct of these home sets in tau. Since tau is enriched, these are objects in C. So these both T0 and T1 are objects in C. And suppose also that C has iterated pullbacks T1 over T0. In their theorem, they don't say iterated pullbacks, they just require existence of any pullback. But I stress iterated because in dimension 2, Grandis and Paré use this iterated, because in higher dimensions, it is more difficult to have existence of general pullbacks, but you often do have pullbacks which are iterated. Okay, so this is just my motivation to put iterated at this place. And also assume that coproducts preserve pullbacks and that the functors, these times with X, objects of tau, preserve coproducts. Well, under all these conditions, which the list seems long, but actually they are not, it's not difficult, they be really fulfilled, a category enriched is also internal in that same category. Well, on top of this, they prove that not only on the levels of categories, but also on the level of the respective functors, there is the analogous kind of assignment. So they proved actually that there is a functor, they denoted by gamma, from the category C cat, which denotes the category of categories enriched over C, into the category of categories internal in C. So both categories and their functors, well, have this correspondence. Moreover, when we co-restrict this gamma to those internal categories, which here I denote with cut sub D, then one gets an equivalence functor gamma prime. What is this restriction of this category? Well, you see that here we constructed T0 as copies of the terminal object. So the internal categories that are of this form, that they're object of objects, is made out of copies of terminal object, then it is called discrete. The object of object is called discrete. So then the internal categories that have discrete, this T0, I mean, the subcategory, right, of such internal categories is denoted like this with this sub D. So co-restricting to them, we have an equivalence. So that was proved in 78. But then later, people realized that something more can be obtained. And now I going to speak about that. What is this more? Now here I will define you the bicategory of matrices, which I denote by CMAT, where C is a category with products and coproducts. So let's see, be like that. And now the bicategory CMAT consists of, for zero cells, we take small sets, I, J, and so on. This small just means actually that they are really sets and not classes. One cells are matrices. So if you take two zero cells or two sets, I and J, then the cardinality of I and J will determine for me the dimension of the matrix. And the entries in that matrix, one entry at the position ij, I denote by M of ij, and this will be an object of C. So it's a rectangular whose ij positions, his entries are just objects in C. And then two cells are family zoomorphisms such that for each coordinate ij, I have a morphism in C, right? So if you imagine two matrices and just among corresponding positions, I take morphisms in C. What is an identity one cell on some zero cell or set I? Well, it is the unit matrix of the dimension, it is a square matrix of the dimension cardinality of I, where now the unit matrix is made out of units and zeros, right? So for the unit, we take the terminal object, and for zero, we take the initial object. This is why we ask that C has products, because terminal object is a specific product, and coproducts, well, specific coproduct yields initial object. And then identity two cell on one cell, which is one matrix. Well, yeah, it is just identity morphism on that matrix. So the family of identities, right? So nothing really big happens there. Now let us see composition of one cells and horizontal for two cells and also vertical. Well, given two matrices, which are two one cells, their composition is given by the matrix. So observe here that first one starts from I, ends up in J, no? So seen as a one cell from zero cell I to one cell J. And the next one starts from J and then ends up in K. And now the total, the composition, will start in I and terminate in K. So this is why you see here this. And each entry is given by the coproduct over this middle index J. Here I read it from right to left. And now given two cells, and that is families of morphisms Ij. So one family is F between M and M prime, and another is G from N to N prime. And also J is here now the middle common index. The horizontal composition of these two cells should be given by a family that starts from I and ends up in K. This is what I write here. Their horizontal composition is given by the family of morphisms HIK, where one HIK for fixed I and K is given here on the right with this red arrow. Well, let us see here, what do I have? So I have these F's and G's, right? So then on a fixed, this product Mij and Njk, I take their two corresponding morphisms among N and N prime G, among M and M prime F, and then on the top I embed into the corresponding coproduct, and on the below also. Remember that these M's and N's, they are all objects in C, and C has coproducts. So I do have these coprojections iotas. So I come here, and now this H is given if you give these morphisms here. So I give them by this composition. And then I have this existence of this unique H. Now, if this would be in two categories, then the square will be non-trivial, but this is just in the one category C, in ordinary category C. I mean, this is the place where I refer to for these morphisms from coproducts and into coproducts. Okay, and now vertical composition of two cells, so one F and one G. Okay, so these are here are taken for horizontal, but for vertical component-wise, it is just the usual, just the ordinary composition of morphisms in C. So now this bicategory of C matrices is clear. Now, what's the point with this bicategory? Well, the point is that enriched categories can be seen as two monads in that bicategory CIMPA. Let us see this. So two monads in this bicategory of CIMPA are categories enriched over C. Let's see this. Well, here I cite this paper where I actually learned this fact, but I guess that this fact was known also before. But in this paper, these authors actually go a step further. But okay, so now first fact, this is this to recover enriched categories. So let's see B with products and coproducts, so one category. Two monads in the bicategory CIMPA consists of, so in black is in a general two category, and in red is in this specific bicategory of C matrices. A zero cell, it is a small set I. A one cell T, well, it is a square matrix, Mij, just over I. And then two cells, mu and eta, well, they are families of morphisms in C of the following form. Well, first from the, so for fixed Ik, we have morphisms in C from the coproduct from Mij to Jk into Maik, and for units, this unit matrix and this Ik component into M, and they satisfy associativity and unity laws. Now to recover a category which is enriched over C, well, we said for this small set I to be some of some tau that we want to be enriched. Then we set for tau AB to be precisely M of Ij, then it is obvious this identification between AB and Ij. And observe that these families of mu's, I mean, one mu given on a coproduct is actually given by another morphism that here I denote by the circle, right? From Mjk, Mij into Mik. I mean, that is implicit, okay? I didn't write it for the eta, okay, for the unit, but I just, write the big things. And having in mind the associativity and unitality, we end up to conclude that this a two monad in the bicategory of C matrices is a category enriched over C. So because tau of AB, it is Mij, it was an object of C. So home sets are objects of C, and the morphisms are actually given by these morphisms, which are morphisms in C, right? Because these mu's were so, and so on, okay? So we recover the two monads in the bicategory CIMPA are indeed categories enriched over C. And now let us sum up what we have at this point. And then I will show you this, what is said in the title, the idea how to recover Ehresmann's result. So first point, we saw that two monads in span of C. At the beginning of the class, we defined like that these are categories internal in C. For this C needed to have pullbacks, okay? And next, what we just did, we saw that two monads in CIMPA are categories enriched over C. For this point, C should have coproducts and products. Well, now I tell you the following result that was proved in this paper. I put in this gray the assumptions. Let V be a Cartesian closed category with finite limits and small coproducts. Then the following are equivalent. That V is extensive, and I don't define that. I just tell you that it involves one preservation assumption on certain functor, and it is very similar to the assumptions of the Ehresmanns, okay? It's just kind of more elegant, so to say, like shortly said. Well, to V be extensive, it is equivalent that an oplex functor int that they define from CIMPA into span DC is a B equivalence. Yeah, so far I told you the bicategory span in C, but not with that index D. In span C that we defined, objects were objects in C. The difference with this D, that stands for discrete, is that in zero cells, we will now have sets, small sets. And then on the levels of 1 and 2 cells, there is an according adjustment made. So that in this way, we have kind of a sub-bicategory of the whole bicategory of spans. Okay, so they proved that under certain conditions, we have a biequivalence among the bicategories of CMAT and discrete spans in C. Okay, so I want you just to have heard this result. So now look at the following argument. Since this int, this two-categorical functor, as a biequivalence preserves monads, I mean, every equivalence will preserve monads, so biequivalence will preserve two monads, two categorical monads. Then, okay, let me state it firstly, literally. Monads in here, in this bicategory CMAT, we prove that they are categories enriched in C. So then we see that categories enriched over C are mapped by this biequivalence int into monads in this span C, which are categories internal in C. Well, actually, since these biequivalents go into spans which are discrete, I didn't write it here, but this image object will be discretely internal category in C, okay? I just forgot to, to put this discrete here in the column. Okay, so we have that on the level of categories, enriched categories are mapped into internal categories by this equivalence. But what about morphisms among these enriched and internal categories? So what about, the question is it true that enriched functors will be mapped by into internal functors by some, convenient biequivalence? That's the question. Because in this way we could recover this result of Ehresmann that they had this co-restriction gamma prime from categories enriched over C. So this is equivalent to the category of discretely internal categories in C. So now we want to have something, some adjustment of this int biequivalence that would include mapping of these functors, which are on one side enriched and another internal. Okay, so now this is our goal. Well, one candidate to try to do this is the two category of monads, well, in a general two category K, and then apply that K is on one hand CMAT and then span in C, right? That is the idea. So there is these two category monads, or two monads in the two category K, where we have 0 cells, which are two monads, and 1 cells were the specific morphisms of monads. 2 cells I don't mention now, and we have defined them in the previous class. So now, if these morphisms of monads show to be internal in one case and another enriched functors, then we are done. Then the restriction of that int biequivalence to the two category of monads in these two respective bicategories would recover Ehresmann's result, okay, under the conditions that should be assumed. Okay, so this is really a little bit involved argument, but I'm really doing my best to show it in the most clear way, and I hope that I manage. Okay, so now let us check if this is true, if this two category of monads is a good candidate in order to recover internal and enriched functors in C. So we actually did it in the previous class, so I will skip these 2 slides. You can just recall these were 1 cells in this 2 category, and the composition was in the other slide. And now, why 1 cells in the 2 category of monads in the bicategory of C matrices are not C enriched functors? Well, there is a slight argument here that I'm not addressing. I mean, also Benaboú didn't, and so on. But you know, to do it really in detail, like much more should be done. But you can believe that this all is true, because this monad in K was defined for K being a 2 category, and CIMAT is a bicategory. So there is a slight, you know, adjustment that you should add these associativity constraints and so on, okay? But up to that, well, which really is not a big deal, we follow the main ideas. So why one cells in the 2 category of monads in CIMAT are not C-enriched functors? Here I first recall what a general one cell in monad should be. It is given by a pair X and psi, where X is a 1 cell and then psi is such a 2 cell, and these two axioms should hold. Now applied to the 2 categories CIMAT, now for these T and T prime, I will take, so remember that T are 1 cells. 1 cells and CIMAT were matrices, okay? So for T, I take a matrix Mij, and since tau are monads, recall that these matrices are square matrices over here over I, and for T prime, I take N, matrix N, that goes over K, so this K will be A prime. And now for this X, I will take, so 1 cell X psi, this pair is given by a 1 cell X in the bicategory of C matrices, which is a matrix X over I and K, because X should go from A to A prime, which are now I and K, okay? And the 2 cell, which should play the role of this psi, which now I denote by F, and this T prime X is now replaced by the matrix N composed by the matrix X, and the codomain is X composed with matrix M. And now the 2 above laws, these ones in the diagrams, should hold. So here we can identify in these diagrams the T's with the M's and so on. But now, if we want to recover C-enriched functors, let us recall what was the recipe to obtain firstly a C-enriched category, and then we will see a C-enriched functor. So a 2 monad in the bicategory of C matrices was a category enriched over C by setting that the set I was object of the enriched category tau. The tau AB was this matrix Mij as an object in C, that we had these morphisms, this circle playing the role of the composition on the matrices. And now enriched functors, this is just a repetition of what we saw before. They need to satisfy these 2 diagrams or axioms. Now let us connect all the information. So now tau AB is identified with these matrices M's. So on the top and the bottom of the diagrams are these matrices M, M, and this C is this circle for the composition. And now F is this that we want to be enriched functor. And now let's go back to our diagram of 1 cells in the 2 category of monads. Well, the diagrams are these, and these T prime and T were these matrices M. And these psi's are these F's. So we would like that these diagrams be the same as these diagrams. But you see immediately that it's not true. So first in the domain, we have 2 objects, and in the codomain 1, while here we have 3 objects in the domain, and in the codomain 2. So here this X is like too much, and also psi goes from the composition of 2 1 cells, whereas here F goes just between single 1 cells. So we conclude that 1 cells in the 2 category of monads in the bicategory of C matrices are not C enriched functors. Whereas zero cell in the two category of monads are C enriched categories. So this two category of monads is not a good candidate for our purpose to recover Ehresmann's result. So now we come to the last topic of today's talk, which will resolve this problem of recovering Ehresmann's result. And that is the double category of, well, two monads, I know, but maybe they should be called double monads, or just say, call them shortly, the double category of monads. Let's see. Well, as you see, this is relatively recent result. And here on this slide, I really cite more or less the text from this paper from the first page, because they really, explain the argument for the motivation. And in this way, I also wanted to show to younger researchers how you follow the arguments and learn about arguments of another researchers. So they say the following: categories, operas, multi-categories, and two multi-categories. Okay, so the three last, you don't know possibly what they are, but they are all categorical structures. Well, all these can be seen as monads inappropriate bicategories. So monads or two monads or pseudo-monads, call it as you want. However, morphisms between these categorical structures are not monad maps in the sense of this classical two category of monads in K. For example, while categories can be viewed as monads in the bicategory of spans, and this is what we saw in our examples, functors are not monad maps therein. We didn't show this, but the argument is pretty much the same as the one that we just saw for the bicategory of C matrices. To address this issue, we define the double category monads in D of monads, horizontal and vertical monad maps, and monad squares in a double category D. So our problem was formulated for bicategories, CMAT and spans in C. And here from bicategories, we go higher to double categories. And then on the double categories, they define these double categories of monads in the double category D. So it seems complicated, but it will serve the purpose that we want. Now, monads and horizontal monad maps in D are exact, so these will be, right, 0 cells and 1 horizontal cells in this double category of monads in D. They are exactly monads and monad maps in the horizontal bicategory of D. Recall that the double category had this on the diagonal in my schematical presentation. It is a bicategory. So the horizontal two category of D. Monads and monads maps in here, okay. While the definitions of vertical monad maps in this new double category and monad squares in D involve vertical arrows of D that are not necessarily identities. This allows us to describe mathematical structures and morphisms between them as monads and vertical monad maps in appropriate double categories. And then, going back to the example from above, small categories and functors can be viewed as monads and vertical monad maps in the double category of spans. So in this way, they resolve this problem that existed with the morphisms of monads with the classical two category of monads in a two category. I want to define you only the vertical maps between monads, but since all this is defined in terms of a double category D, then the diagrams are different than the ones that we used so far. They use these square diagrams because in double categories you also have non-trivial vertical one cells. So here C in their article is a double category, and now as first gadgets or as objects of the double category of monads, they define monad. Don't read the text, just follow my arguments and the diagrams. So for us that we saw so far, two monads in a two category were one cells which act on the same zero cell, and we had two cells mu and eta, satisfying associativity and unitarity. Where here happens precisely the same thing, just written with different drawings. And okay, letters are also different. Here these X in the vertices are what I denoted by A's. These are the zero cells of the double category. What I denoted by T, that stood for monad, one cell, here is denoted by P, and they are horizontal one cells. So here we have PP in the domain and in the codomain P. As vertical one cells, they put just identities. So we are really living in a bicategory and not in a double category. And now the whole square is this mu, and similarly, the arguments go for eta, so that mu satisfies associativity and also eta satisfies the unitarity with respect to mu. So I just wanted to show you that you can also draw these axioms for monads that I wrote with string diagrams. You can draw them with these diagrams for double categories. And now vertical monad maps between two monads, one xp, other x prime, p prime. Don't read the text, just follow my words and the diagrams. So first you apply this two cell mu from PP into P. So here below they don't write the names of the one horizontal one cells, but I'm saying you on the top you have P and P, PP composed. In the middle, horizontal is also P. So the two cell mu went between them. And then goes a square, which is denoted by U bar. Now on the left vertical, from X to X prime, goes a non-trivial vertical one cell called U, which they here don't write, but I tell you it is called U. It's this U here on the top. And on the right is the same U. So on the top is P, or in the middle, and on the bottom is P prime. So that is a non-trivial square. This should be equal to set these square ones, another ones horizontally composed, and at the bottom put this mu multiplication for the second monad. And for the identity similar, so first unity, then this non-trivial two square. This should be equal as just applying practically. So here identity on U, the vertical one cell U, and then this eta. Good, but now when you consider a bicategory and then you embed a bicategory into a double category, then you will have that vertical one cells are all identities. So then in all these squares, so these two axioms, you will have these diagrams that you can actually you can make their left vertices, all the left vertices coincide, and also all the right ones. So that actually you have some two identities of two cells in a bicategory. And what do they say? They say first multiply and then map by some two cell U. It's the same as applying U, tensor U, and then multiply. And second, the unity and then U is the same as just unity in the other monad. And these are precisely the common axioms for, well, in this case, for enriched functors, which, if I remember well, was somewhere here. Yeah, this is these below diagrams. So here is multiplication, and then map is the same as map, tensor map, and then multiply. Okay, so these are these usual axioms, and we conclude that vertical one cells in the double category of monads, in the double category obtained by embedding the bicategory of C matrices into the corresponding double category. So it's a complex formulation, but I hope that you can follow more or less. They are indeed C enriched functors. So this double category of monads resolves the problem. And this is my last slide where I sum up how to recover Ehresmann's result. So we saw before from this paper of Power, Fuji, and I don't know the other one, the oplex functor int from the bicategory of C matrices into discrete spans was the equivalence under certain conditions, okay? And if we went from there to the two category of monads of the respective two categories, we could not recover Ehresmann's results. But extending from the bicategories of C matrices and spans to pseudo double categories of C matrices and spans, this oplex functor from above extends to a double functor, which I call it internal, between these respective pseudo double categories. And one obtains the following theorem: let V be Cartesian closed category with finite limits and small coproducts, then it is equivalent that V is extensive on the one hand, and on the other that the double functor, this one that I obtained here above, is a double equivalence. So now consequently, if you concretely consider here zero cells and vertical one cells in these double categories, you recover that if C is extensive, Cartesian closed with finite limits and small coproducts, then there is this equivalence, and it actually coincides with the same functor of Ehresmann's, which they denoted by gamma prime, from the category of enriched categories into that of discretely internal categories. So I think that this is really a beautiful, although involved, construction and argument, but this is what I want to. Yeah, I'm finished. Thank you for your attention.
Because the time is over.
Yeah, I finished. Thank you.
Questions? Yes. Questions? Okay, Bojana, we thank you for your classes, and I'll speak with you after WhatsApp. Thank you a lot.
Okay, thank you for your attention. Bye.